Okay, so this lecture we're gonna go back to compactness and the Euclidean spaces. And the very last time, we have proven the theorem is that the closed interval in R is compact, right? And so now we're gonna prove another theorem called Heine-Borel, which is a very famous and important characterization of compact sets, compact spaces, and Euclidean space. So the statement is that if it's compact, if and only if it is closed and bounded under the Euclidean or square metric. Okay, it's closed and bounded under either metric. First, we have the inequality here implies that A is bounded under D if only if it's bounded under both. It's bounded on the Euclidean metric if only if it's bounded under the square metric. So we just check the square metric. Okay, of A being compact, we can pick an open covering of A by open balls, because A is compact, so there exists an exactly one such that A is contained in one of them. Well, this really implies that A is bounded. A is closed because R is metrizable, right? So hence is Hausdorff. And metrizable spaces are Hausdorff. You can check it by triangle inequality. Conversely, suppose that A is closed and bounded. So first we pick a bound, right? We pick a bound n such that rho xy is less than or equal to n for any xy and a. Now we fix an element x naught in a. Now we define b as distance from x naught to the zero origin in Rn. Then by triangle inequality, we have all the x naught is in n plus b. So from here, we see that x is in the cube, right? Is in the n cube, right? Because we're interpreting by the square norm, right? From here, it means this. So x is in a compact set, because finite product of compact set is compact, right? This is compact because closed interval is compact, and product of compact is compact. So A is closed, subset of a compact set implies that A is compact. So here we have proven the important Heine-Borel theorem, right, in Rn. Now, next we're going to prove another important theorem, which is called extreme value theorem, EVT. So it states that given x compact and y with the order topology, then for any continuous function from x to y, it attains maximum. So what it means, a maximum and a minimum. What it means is that there exists C, D, and X such that FC and FD is the lower bound and upper bound for all the other inputs for any X and X. It attains its minimum and maximum, provided that X is compact and Y is topology. And this proof is really easy because it's compact, right? Fx is compact, right? We can just assume by contradiction it has no largest element. Then we consider this open cover, right? It's an open cover, so it gives a finite subcollection that also covers A, right? Now, for A1 to AN, if A is defined as the maximum, then we have this covers A. But A is not in this interval, but this A covers A, which means that A should also be inside this interval, which is a contradiction. For minimum, it's similar, right? So A must has a maximum, right? So this is the extreme value theorem. And move on to next. We will prove the uniform continuous theorem. So before that, let us introduce some basic definitions. So given a metric space in a non-empty set, we define a distance from X to a set is the infimum of all dxa for A in A. Okay? We define it as the closest distance, so the distance between point in a set. So if we fix A, then the function that sends X to the distance between X and A is a continuous function. Okay? And recall that also A is bounded, we define the diameter of A to be the supremum of all distance inside it, distance between 2 points inside it. So diameter of A. Okay? So here comes the lemma, Lebesgue number lemma. So the statement is that given any open cover of a metric space, if this metric space is compact, then there exists delta such that for any subset of X with the diameter is less than delta, it is contained in exactly one open set from the open cover, right? So this is the theorem. Provided that X is compact, then there exists a cutoff delta such that as long as your diameter is less than delta, then you're contained in exactly one element from the open cover. So if X is in the open cover, then any delta will works, right? So we suppose that X is not an A. So we admit a finite subcollection covers X. We define Ci as their complements, and see where we're going to use the Ci's. So first we define a function that from X to R such that fx is the average of X to Ci, and then we divide by n, which is the average, the distance between X and Ci. Okay, so we take their average. Okay, after we take this average, right? Because fx is positive, since for any x it must contain an AI. And AI is open, so a ball is containing an AI, right? If it's a ball, then distance from X to Ci should be at least epsilon, right? You can argue this, right? Because if you're an AI and your X, you have a ball, right? To reach Ci, you must at least, I mean, okay, like you get the idea, right? Give it X, get a ball X, to reach Ci here, this is Ci, right? You must at least go beyond this distance first, right? So this is true. You can check it by definition, which is lengthy, so I admit it. So fx is positive. And also, fx is continuous function, right? Because in R, because sum of continuous function is continuous, right? And we multiply by a scalar, doesn't matter at all, right? So f is continuous on X. We admit a minimum. Well, this delta works. The minimum works by EVT. Why? So here it comes. For any subset with diameter less than delta, x0 is in K, which means that if you're in K, for any elements in K, the distance must be less than delta, right? So for any B and K, d of Bx is less than delta. This precisely means that K is in the delta neighborhood of x0, right? So the subset with diameter less than delta, it is contained in the delta neighborhood of some x0. Now, delta is the minimum. It is less than the average, of course, right? And it's also less than equal to the maximum, right? The maximum one, right? This is defined as the maximum of dxci. So from this inequality, we see that the delta neighborhood of x0 is contained in AM for this corresponding M. So here's why, because we do it by contrapositive. Suppose y is not in AM, we will show that y is not in x0 delta. If y is not in AM, then you're in CM. If you're in CM, then y in x0, you're in CM, right? So the distance between y and x0 must be greater than the infima, right? Greater than infima, but this is greater or equal to delta. So this is greater or equal to delta. So distance between y and x0 is greater or equal to delta, so you're not in the delta neighborhood of x0. So here we prove that, right, K is contained this and K is contained in AM. So here we prove the Lebesgue number lemma. And we're going to use this to prove the uniformly continuous theorem. So given any function between metric spaces that is continuous, if the domain is compact, then this function is uniformly continuous. So first we just cover y by the epsilon over 2 neighborhoods. We take A to open cover X by taking the pre-image of all the balls in Y. and we pick delta, the Lebesgue number of A. This is always doable because X is compact, right? The Lebesgue number states that for any open cover of metric space is compact, then we have a Lebesgue number, right? So here we cover Y, and then we omit a cover of X by open cover because F is continuous, right? So the pre-images of balls are open. So we have an open cover of X, so we can pick a delta, the Lebesgue number, right? So if 2 points is less than delta, the distance, the diameter of this set, right, is less than delta, which means that you must contain in some single open cover, right? Single open cover. This means that from here, means that fx1 and fx2 must be in here. And from here, we use triangle inequality. We show that their distance is less than epsilon, right? So for any epsilon, there exists in delta such that this implies this uniform continuity, right? And lastly, we're going to prove something that is not topology, but something that is interesting. We're going to prove that R is uncountable, not using decimal representation and something else. We're just going to use the topological property of R, and to prove that R is uncountable. Well, let's see how it works. So before a definition, a point is an isolated point if the singleton set is open in X. Okay, given a space. So remember, with this definition, we're going to prove the theorem. The theorem states that given non-empty compact Hausdorff space with no isolated points is uncountable. Okay, so first I have a claim. So this claim states that for any non-empty open sets and any random point in a space, there exists another non-empty open set such that it is not contained in the closure, but this open set is contained in U. Okay, so this doesn't seem like intuitive at the first time when you see it, but you don't really need to. We just need the result that X is uncountable, okay? So this is the claim. And to do this, we can first pick Y that is not equal to X that is in U. This is possible because if X is in U, since it has no isolated points, so this is not open, right? So U cannot be equal to X. So we can so it definitely must be properly contains this point X, right? Right. If it's not clear enough, let me explain it again. So if X is in U, since this is not open, so this is not a neighborhood of X. But we say that X is in U, and U is open, so U is a neighborhood of X. U is a neighborhood of X. But this cannot be a neighborhood of X, so U cannot be equal to X, right? They cannot be equal to each other. But X contain in U, which means that this is subset of U, right? So this is properly contains X. So we can find another Y that is not equal to X that's in U. Okay, so this is the case if X is in U. Well, if X is not in U because U is not empty, we can pick a Y, right? And this is not equal to X because X is not in U and Y is in U, right? Okay, so first we pick a Y that is not equal to X that is in U. Because this Hausdorff, we have the disjoint neighborhood such that we pick V as W2 intersect with U. It's an intersection of open set, so it is open, and V is contained in U, right? From this definition, it's contained in U. So, and W1, okay. So, this W1 intersect V is equal to empty, right? Because W1 and W2 are disjoint, right? So W1 intersect V will give you an empty set. So for this X, it has a neighborhood, right? W1 is a neighborhood of X such that it is disjoint with V, this implies that X is not in the closure of V. Now, so we have proven the claim. Okay? So now, given any sequence in X, we show that it is not surjective. This implies X is uncountable. Why? Because given any sequence in X, right, it is not surjective, which means that it is uncountable, right? So if this is not like intuitive at the first time, if you do the contrapositive, right? So if X is countable, there must exist a sequence such that it is surjective, right? Bijective implies surjective, right? If it's countable, then you be able to establish a correspondence, right? But we show that none of the sequence in F is surjective. So none of them are bijective. So you cannot establish a one-to-one correspondence, a bijection between the X and the natural positive, natural numbers, whatever you said, right? The same. Okay. So we show that any sequence is not surjective. First, by claim 1, we let U be equal to X, then we have a V1 and X1 does not end in V1, right? For this X1, right? So in general, given Vn minus 1 open non-empty, we can pick another open Vn that is contained in Vn minus 1 and this point Xn that is not in Vn bar. Okay? So first from here, we have that okay, from here, this is a nested sequence, right? 1, 2. So V1, okay, if this also works, right? So V1 bar contain V1, 2, blah, 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 is not empty closed sets, right? Because X is compact. X is compact, the intersection must be non-empty. So you can pick a point that is in the intersection of all of those. Then if you're in all of them, because X1 is not in V1, Xn, blah, 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 Xn is not in Vn, right? So if X is in all of them, then you're not supposed to be equal to any Xn. Thus, it is not surjective, right? Because you're given a sequence, Xn equal to Fn, any sequence, you can find another X that is not inside Xn, right? This X is not in the right, it is not in the image, so it is not surjective, right? Which proves that any non-empty compact hollow source space with no isolated point is uncountable. As a corollary, closed interval in R are uncountable. Why? Okay, closed intervals, yes, they're non-empty, they're compact, they're hollow source space because they're metrizable, right? And has no isolated points, right? So it is uncountable. Why it has no isolated points? Bro, basically, like if it A, B, right? Let's draw a line, A, B, if A is open, the complement will be A, B, that it is not open nor closed, right? And if this point X is open, then the complement will be this, right? Which also not closed, right? So it has no isolated points. Hence, closed intervals in R are uncountable. And this is everything for this lecture. Okay, so see you guys next time.